Hello, my dear students. I am Arthraj Chakraborty, lecturer in electrical engineering of Sri Ramakrishna Institute of Science and Technology. Today, I am going to solve some important problems related to single phase transformer. So, at first, the numerical of EMF equation is solved here. So we can see the first numerical here. 3300 by 250 volt 50 Hz single phase transformer is built on a core having an effective cross sectional area of 125 centimeter square and 70 turns on the low voltage winding. Calculate the value of the maximum flux density and the number of turns on the high voltage winding. So here the given data are E1, that is the primary supply voltage or EMF, that is 3300 volt, E2 that is 250 volt, F equals to the frequency, that is equals to 50 Hz, A is the area of cross sectional area of cross section of the core or effective cross sectional area of the core, that is 125 centimeter square, equals to 125 into 10 to the power minus 4 meter square. We know the secondary induced EMF E2 equals to 4.44 phi m F into T2. So here 4.44 phi m means the maximum flux. We know that maximum flux equals to flux density and the product of area. So 4.44 Bm into A into F into T2. So at first we have to find out the value of maximum flux density, that is Vm. From this equation we can write that Bm equals to E2 by 4.44 into area into frequency into T2. Okay. So 250 by 4.44, area is 125 centimeter square, that means 125 into 10 to the power minus 4 meter square. So 125 into 10 to the power 4 meter square into area into frequency is 50 Hz and 70 turns on low voltage winding. That means here it is a step down transformer. You can see here it's a step down transformer because the primary voltage is 3300 volt and secondary voltage is 250 volt. So the secondary winding, that means the low voltage winding, number of turns is 70. So T2 equals to 70. Okay. So it is equals to 1.287 Tesla or Weber per meter square, that is the flux density. So from that equation we can find out the flux density. And the second part of this math is we have to find out the number of turns on the high voltage side. We know that U1 by E2 equals to T1 by T2. So E1 is 3300 volt, E2 is 250 volt and T2 is here 70 number of turns. So T1 equals to E1 by E2 into T2 equals to 3300 by 250 into 70 equals to 924 turns. So the primary turns or high voltage turns equals to 924. So that is very simple. That is the first numerical problem we have discussed here. Now in the next slide we are going to solve another very simple problem of single phase transformer. So the statement of the problem here: a transformer with 800 primary turns and 200 secondary turns is supplied from 100 volt AC supply. Calculate the secondary voltage and the voltage per turns. Okay, it is very simple. So according to this problem, the given data are T1, that is the primary turns, 800, T2, that is the secondary turns, that is 200, V1, that is the supply voltage, that is 100 volt. Okay, so we know that V1 by V2 equals to T1 by T2. So V2 equals to V1 into T2 by T1. V1 is equals to, we know that 100 volt, that is supply voltage or primary voltage. So 100 into T2 by T1, secondary turns is 200 and primary turns is 800. So 200 by 800 equals to 25 volt. So the 25 volt is the secondary side voltage, and the voltage per turn, we know the primary voltage is 100 volt. So in case of primary side, the voltage per turn is equals to 100 by 800, because 100 volt is the supply voltage and primary turns is 800, equals to 0.125. And in case of secondary side, the per turn volt equals to V2 by T2, that is V2 equals to, we know that 25 volt, T2 equals to 200 volt. So 25 by 200 equals to 0.125. Okay, so 0.125 volt per turn for both these windings of this transformer. So from this numerical, we know that the voltage per turn for any transformer, for any side of winding, a primary side or secondary side, it is always same. Okay, so that is the numerical number 2. Now we are going to solve a complex problem, that is the numerical number 3. Okay, so at first we have to read the statement of the problem very clearly. A single phase 250 by 500 volt transformer gave the following results. So at first we know that the transformer is single phase 250 by 500 volt, that means it is a step down transformer. 250 volt is the primary winding voltage or low voltage winding voltage, and 500 volt is the high voltage side voltage. Give the following result. Open circuit test result is the result from voltmeter, that is 250 volt. Ammeter result or ammeter reading is 1 ampere and wattmeter reading is 80 watt. That means 250 volt is the supply voltage, 1 ampere is the no load current. We know that from open circuit test we can get it, and 80 watt is the iron loss on LV side or low voltage side. And the short circuit test results is 20 volt is the short circuit voltage, 12 ampere is the short circuit current or full load current, and 100 watt is the I square R loss or full load copper loss on HV side. Calculate the circuit constant and show them on an equivalent circuit. So we have to find out the circuit constant or circuit parameters. So from open circuit test, the result is V1 equals to 50 volt, I0 equals to 1 ampere, and Pi, that is the iron loss, equals to 80 watt. So we know that P equals to, or loss equals to, or it is the power loss equals to V1 into I0 cos phi 0. V1 supply voltage, rated supply voltage, I0 is the no load current, and cos phi 0 is the no load power factor. So cos phi 0 equals to Pi by V1 into I0. So Pi is the power loss or iron power loss or iron loss. So 80 by 250 into 1 is the I0 value of the, so it is equals to 0.32. So cos phi 0 equals to 0.32. So we know the parameters are IW, that is the working component, I mu, that is the magnetizing component of current, both are the component of current. R0 is the resistance of the core and X0 is the reactance of the core. So IW equals to, the active value of current or the real part of the current, okay, or the cos component of the current, that is I0 into cos phi 0. So I0 equals to 1 into 0.32 equals to 0.32 ampere. And I mu is the sine component or reactive component of the current, okay, which is responsible for the hysteresis loss, and IW is responsible for the eddy current loss. So IW is responsible for eddy current loss and I mu hysteresis loss. So it is equals to I0 square minus IW square, okay, equals to I1 square minus 0.32 square equals to 0.947 ampere, okay. And R0 equals to, we know that V1 by IW, that is 250 by 0.32. R0 is the resistance of the core, okay. From the resistance this IW current is flowing, so R0 equals to V1 by IW, and from the reactance this I mu current is flowing, so X0 equals to V1 by I mu equals to 264 ohm. So value of R0 is 781.25 ohm and value of X0 is 264 ohm. Now the short circuit test, as the primary is short circuited, here you can see that short circuited, therefore all the values referred to the secondary winding. The results of the short circuit test are given on term of HV side, while the results of the open circuit test are in term of low voltage side. The results obtained in short circuit test are therefore converted in terms of LV side, okay. So we know it, so that here 20 volt is the short circuit voltage, okay. PCFL, that means power loss, full load copper power loss, equals to 100 watt full load copper loss, and I2SC, that is the short circuit current, that is 12 ampere. So, and we know the turns ratio T1 by T2 equals to, that is step of transformer, so T1 by T2 means 250 by 500, that is 0.5, okay. So voltage applied on the LV side, so V1 is equals to, we know that the value of V1 is C equals to V2 SC into T1 by T2, okay. So that is 10 volt in V1 SC equals to 10 volt, okay. Now I1 SC equals to I2 SC into T2 by T1, that is 12 into 500 by 250 equals to 24 ampere. So PCFL equals to I square, that is I1 SC square, that means the 10 ampere. Actually in this case the short circuit test is performed, you can see here, on the HV side, okay. These values are measured in the HV side, not in LV side. Actually the HV side is connected with the windings and LV side is short circuited in case of short circuit test. So these instruments are on HV side. So when the instrument are on HV side and the turns ratio, if we multiply the turns ratio or with that value, so we can get the value of that is the referred to secondary. If we measure the value of referred to secondary, then this is I1SC, and we are getting these values of the current, voltage, impedance, resistance and reactance in referred to secondary. So the V1SC equals to V2SC into T1 by T2, 20 into 250 by 500. Okay, so 10 volt. So I1 is equals to I2SC into T2 by T1, because we know that V1 by V2 equals to I2 by I1 from the equivalent circuit. So 12 into 500 by 250 equals to 24 ampere. Okay, now PCFL equals to I1 square into RE1. So RE1 equals to PCFL by I1SC, that is equals to 100 by 24 square, that is equals to 0.1736 ohm. ZE1 equals to V1SC by I1SC, that is 10 by 24 equals to 0.417 ohm, and XE1 equals to root over ZE1 square minus RE1 square equals to 0.417 square minus 0.1736 square equals to 0.379. So that is the value of XE1. Okay, so these all values are referred to secondary, not referred to primary. Okay, you can see here as the primary is short circuited, therefore all the values referred to the secondary winding. Okay, because this transformer is a step up transformer. If this is a step down transformer, then the values are calculated in referred to primary. Okay, so now we have to draw the equivalent circuit. So that is the equivalent circuit. That is the primary voltage 250 volt supply voltage plus open circuit test. That is the value of the R0, that is the resistance of the core, 781.25 ohm. That is the reactance of the core, X0 equals to 264 ohm. That is the no load current, that is 1 ampere. That is the value of RE1, or the resistance referred to primary, referred to, that is secondary, sorry, that is referred to secondary, because the here this transformer is step up transformer. So the value of RE1 equals to 0.1736 ohm and XE1 equals to 0.379 ohm, and short circuit current is 24 ampere. Because in that case of this for this numerical problem, in case of short circuit test, the primary side is short circuited, because the primary side here it is the low voltage side, and according to the short circuit test theorem, we know that the low voltage side is short circuited. Okay, and in case of this transformer, the secondary side is the high voltage side, so we have to calculate the value referred to secondary. Okay, now the last one, or the last numerical problem. A single phase transformer working at unity power factor has an efficiency of 90% and both half load and at the full load of 500 watt. Determine the efficiency at 75% and full load and maximum efficiency. Okay, so efficiency equals to, we know that output by output plus losses, or output by input. We know that input equals to output plus losses. So in transformer, the full load efficiency equals to V2I2 cos phi, this is the output, and input equals to output plus losses, that means V2I2 cos phi plus iron loss Pi plus full load copper loss. So here we can see that, so efficiency is 90%, that is 0.9 per unit, equals to the full load power or the power output is 500 watt, so 500 by 500 plus Pi plus PCFL. So in case of half full load, that is V2. When the load is half, then load current is also half, so V2 into I2 by 2, so into cos phi in case of half full load, and that is V2 I2 by 2 cos phi Pi. The current is also half, so 1 by 2 square PCFL. Okay, that is the I square R loss, so that is square, current is square, so 0.9 equals to, that is 250, 500 by 2, that is 250, that is also 250, and 1 by 2 square, that means 1 by 4 PCFL, and Pi or the iron loss is constant, because iron loss is depends upon voltage, not upon current. So when the load is half, then the voltage is not changed, the load current is also half. So from this equation we can write that 500 plus Pi plus PCFL equals to 500 by 0.9 equals to 250. That is the first equation, that is E1 241, that is E242. So the first equation, that is from here we can write that 500 plus Pi plus PCFL equals to 500 by 0.9. okay, and that is 250. From this equation we can write that in both two cases, okay, in the both two cases the efficiency at first is 0.9, and after that the efficiencies remains unchanged. Okay, efficiencies remains unchanged, so it is equals to, we can write that 250 plus Pi plus 1 by 4 PCFL equals to 250 by 0.9. Solution of this equation, we can get that PCFL equals to 37.04 watt and Pi equals to 18.52 watt. Okay, so these are the value of iron loss, that is the Pi 18.52 watt and full load copper loss 37.04 watt. Okay, and efficiency at 75% full load, that is 75% means 3 by 4, 100% is the maximum percentage, and 75% means 3 by 4, so 50, here it is that 500 watt is output power. So efficiency equals to, we know that output by input, or output plus losses. Okay, input equals to output plus losses. So here it is 75% full load, that means 500, that is the output power, into 3 by 4 by 500 into 3 by 4 plus Pi plus 3 by 4 square PCFL, that is I square R. Okay, equals to 375 by 375 plus 18.52 plus 9 by 16 into 337.04, that is equals to 0.905 per unit efficiency at 75%. So output at maximum efficiency, so the output of maximum efficiency equals to, we know that the total power output into root over Pi by PCFL, so that is equals to 500 into root over 18.52 by 37.04 equals to 353.55 watt, that is output at maximum efficiency or power output at maximum efficiency. And we know that at maximum efficiency the copper loss is equals to the iron loss, so PCFL equals to Pi. So the maximum efficiency equals to the output power of maximum efficiency, that is 353.55 by output plus losses. So output is 353.55 plus PC equals to Pi, so Pi is 18.52, so PC is also 18.52. So maximum efficiency equals to 353.55 by 353.55 plus PI, that is 18.52 watt, that is iron loss, plus we know that copper loss equals to iron loss, so plus 18.52 watt equals to 0.9051 per unit efficiency. Okay, so we can find out from here the efficiency at 75% full load and the maximum efficiency. Okay, that's all. Thank you.